Welcome back, everybody, and welcome back to this session on advanced machine learning, physics 5429. I wanted to give you some messages in the beginning here, and anyway, also feel free to unmute yourself and ask questions, or just put questions in the chat, and I will try to answer them as quickly as possible. The messages I wanted to give you obviously about where you find material, and about project number 1, or the first tentative sketch of project number 1. And I wanted to discuss the layout for the project and the type of tasks which we can work and discuss on. And then the topic for today, besides discussing the project itself, is actually to get started with convolutional neural networks. So I'm assuming that most of you are familiar with the basics of neural networks. And now we're going to jump into the domain of convolutional neural networks. And after that, the plan is to look at recurrent neural networks. And if we, when we're done with that, it's autoencoders and generative adversarial networks. And that will keep us busy before the break, which we have due to the Easter vacation. Now, the other type of information I wanted to give you is typically that you find the slides linked here, and we're going to discuss them. We're going to jump a little bit back and forth between the whiteboard and the slides. You will find the video a little bit later. This same information here is also linked up in the at the University of Oslo website for the course, in case you may have forgotten about this. So we have an official website, which is this one. And let me just bring it up in the chat here for those of you who may have forgotten about that. So I'm just going to put the link in the chat here so you have it. And there are some features there which I actually wanted to remind you of in case you have forgotten it. So I should have reminded you about this in the very beginning. So if you click on the spring 2023 and go to the schedule link. So the schedule link here has a list over the sessions which we have for the semester with a kind of tentative plan. And after each lecture, you will find the video of the lecture here as well. And this is a service which you can also subscribe to. So it should actually have been in English, because I came from an English site, but by some odd reason, it doesn't translate into English. I hope you can forgive me for that. This is beyond my control, actually. So I've chosen English as a language, and you can see here, the language here is partly English and partly Norwegian. But this link which you see here, you can actually subscribe to these activities. So that means you get a message every time there is a small change here. And that can be useful. And it will also flag to you when the lecture videos have been uploaded, which is normally right after the lecture. And also on this page here, you find the weekly messages about the plans. And then also the down here, you will find the link to the GitHub address again, which you all have access to. So this was a little bit about practicalities, in case you've forgotten about this. There's also another thing I wanted to quickly remind you about, is if you click at the GitHub link, and let me paste this again back into the chat in case you have missed it. So you have the link here. Now, if you go to the to this doc folder, which you see up here, and you click into this project folder, you will then find the first attempt at the description of the project, either as an HTML file, a Jupyter notebook, or if you prefer to use LaTeX and a PDF, you have the LaTeX source file for the project. So what I wanted actually to do now is to look at the project description, and then we are going to jump into the Jupyter notebook for today. So this is also the material you have access to. And in this particular notebook, you will find the description of the tentative paths for project number 1, or what could just become a big project. So we are going to be pretty flexible about the way we look at the projects here. I will also, when you have, based on the kind of inputs you have, I'm going to suggest project groups in case you want to collaborate with other people. So I'm going to send an email to all of you based on your feedback on the form which we had. And based on this feedback, I'm trying to suggest the project groups. But you should also feel free to email me personally in case there are specific persons you want to collaborate with. So the material today is mainly going to rotate around convolutional neural networks, and I'm coming back to the basics of that a little bit later. But then we're going to look at the projects and the different possibilities which we have. So I'm going to suggest 4 different paths, and you should see which one fits you best. So there's something which I call the computational path. And this is for those of you who would like to write, let's say, your own code for a convolutional or eventually a recurrent neural network and apply this to data of your own selection. And the code in that case should be object-oriented and flexible, allowing for eventual discussions or extensions by including different loss and cost functions and other functionalities in much the same way as we discussed in connection with the neural network codes. So in this case, you can also feel free to suggest your own data sets. So this would be more kind of path where you want to develop a code for, let's say, convolutional neural networks or eventually recurrent neural networks. And if you want to dive into autoencoders, this is also something which is fully possible. I think writing a code for general adversarial networks is something which will take much more time. So I would not recommend that. Alternatively, if you're interested in topics like Monte Carlo simulations and Boltzmann machines, there's also a possibility to develop a code on Boltzmann machines. So you should feel free, in a sense, to suggest paths which are close to your interests. Then the path which is a kind of mix of the first one here. So you can actually, in this first path, you can actually look at the differential equations, which I'm suggesting here. And this is a topic which I will use as a kind of example in the lectures. So for convolutional neural networks, I'm not going to look much at the differential equations. Then it's more imaging, which is the main topic. And that is also where convolutional neural networks have had an immense success. So in this particular case, we are going to look at a given set of differential equations. And in the first attempt, which we are looking at, these are ordinary differential equations, but we can easily extend this to other types of differential equations. So this is in a way to just get you started. And thereafter, we plan to extend the set of methods to recurrent neural networks and eventually autoencoders and/or GANs. And all these approaches can be expanded into one large project. And then you would present this at your final oral presentation. And here you can also add things like including physics-informed machine learning. You can discuss neural networks that are trained to solve supervised learning tasks while respecting any given laws of physics described by general nonlinear partial differential equations. So we could now focus on things like the Navier-Stokes equations, if that is something which aligns with your research, or other types of differential equations. Then there is another path, which I call the application path. And in this specific case, there may be data sets which you want to study, which are relevant for your research. Suppose you have an imaging project, then it would be more interesting to actually use existing software, like software which you would find in libraries like TensorFlow or PyTorch or similar ones, and then use that on applications on specific physics problems. Just to give you an example, if we go back to the GitHub folder, which we have for the course, and if you go into this link called earlier projects, you will find examples of exactly that. And this is a path which I call the application path. And in this case, there were students from high energy physics, which looked at the Higgs challenge, and also on the reproduction of images from data from detectors on weakly interacting particles, or so-called WIMPs, as they are called as also. And these are examples. You can look up these projects of what I would call more the application path. So if we now go back to the Jupyter Notebook here, this is another possibility. So that means this is more you being on your own and defining your own data set, and you just work on that one together with other people if that is of interest. And then you just go through your data and wrap up a report along the same lines as those which you saw in that folder. Then there is a path here which we may not cover after the break. And this is about Gaussian processes. For those of you who are actually working with that, this is something which you could think of starting with immediately. We won't cover that in the lectures before, eventually after the Easter break. However, if you are familiar with some of these topics, this is also a path which you could explore independently of the lectures which we are giving here. And this is also a path, this number 4 here. You can actually opt to actually look at the solution of differential equations as an example, and then modify the second part of this path 2 here, the differential equation path, and apply, let's say, Bayesian kernel regression or Bayesian machine learning applied to the solution of these differential equations. Now, the advantage with the Bayesian approach or Gaussian processes, which is a very common implementation of these, and topics like kernel regressions, etc., that is that this allows you to quantify the errors in the parameters, the optimal parameters of the model which you have chosen. And that means that when you make a prediction, you have also an estimate of the errors of the prediction. And that's extremely useful. So if you think of standard machine learning, the way it's normally described in many implementations, you're often interested in just using data to make a function approximation or to be able to make predictions, and then on data which have not been used in the training. And then you may also be interested in finding correlations among the different features in your data. As an example, if you're looking at the housing data and the price of a house, you would typically find that the price is strongly correlated with the number of rooms the house has, the size of the house, etc., etc. So these will be parameters or features which play an important role when you study correlations in a data set, and which also allow you to say something about what kind of features you should include in making predictions. Now, all of this, which follows the standard machine learning axis, falls under what's normally called a frequentist approach in statistics. It means that often we can or we are not that much interested in a probability distribution behind the data we are studying. We can extract it from a frequentist approach, but it is less common to do so. Whereas if you use a Bayesian statistics, it's an approach where you can make both predictions. You can also find or study correlations in the data. And at the same time, you can estimate the errors of the parameters which you have optimized in order to find the best possible reproduction of the data. And you can also study causations. What is the probability of A given an input B? So if this path 4 is a topic which you're interested in and you want to start with that immediately, you would be a little bit more on your own, because we will focus more on deep learning in the lectures. However, this is something which we could pick up after the Easter break. And then we could look at how this can be used in, for instance, either this computational path or the differential equation path. So these are the kind of paths I would like to suggest. And since this has been a kind of self-study course, it means that there is the possibility for lots of independent work. Or if you now want to follow what I'm suggesting, this is the alternative 1 and 2. You could combine the two, depending on how much time you want to put into it. There are lots of data sets which you can pick if you want to, or if you have data from your own research. And you should try to link if these data have been analyzed when you write the report. You should try to see if there are scientific articles which discuss the data sets which you may eventually end up choosing for the projects. And there's a link here to Physics SDK 4155, where you can find a kind of instruction on how to lay out your report. So what I wanted to look at now is what we might call the first step in this either path 1 or path 2, and the kind of data set which we can actually generate. And this is also a data set which we can use, or a set of equations which we can use in recurrent neural networks. And also, if we want to look at autoencoders and GANs, we can actually keep using this data set. And these are the methods which I will try to focus on in the lectures which come till we reach the Easter break. And the set of equations is a famous set of equations. It's called the Lorentz attractor model, which has been studied since the 1960s. And it is a famous model which is used to study chaos in differential equations. And these parameters which you see here, sigma, rho, and beta here, these are just parameters, and I've chosen those which many people have used in the literature in order to study this type of equations and chaotic motion. So the differential equations are equations for x, y, and z, and you see the equation set up here. Now, what we are going to do now is to generate our own data, and with our own data, we are going to use these to make inputs and outputs data for a neural network training, so that we could actually make a prediction of what the solution X, Y, and Z look like without having made a calculation for that specific time step. We're actually going to run the calculation, produce a large data set, and then we're going to use that data set to see if we can reproduce what comes from the data set here. So in this specific case, there's a function which I placed in the lecture material for this week. And this function simply uses the differential equation library, which follows NumPy and Python. It's called ODInt. And I fixed the time step to delta t, 0.01, and then there's a final time here. And the program, what that is doing, it fixes 100 random initial values and produces inputs and outputs for a neural network. So when you solve a differential equation, what we are doing then, we are finding x. So x is an array which contains x, y, and z as functions of time. And you will produce this solution as a function of the time step. So x is going to be an array which contains then time, x, y, and z. And this solution which you get by solving an ordinary differential equation, and typically this will be a Runge-Kutta to four-folder, is producing this x of t. This x of t at a given time step is going to define, with these random initial values, is going to define your input to a neural network. And then you know that the input to the neural network actually, or the input to the differential equation or the previous time step, is used to produce the next time step. So let me just quickly remind you of that basic strategy of ordinary differential equations. So let me just bring this up in the Jupyter, in the whiteboard here, so you can see the way we are setting up the data here. So if you're thinking of a differential equation, what you will have then is typically, so I'm setting this up as an ODE, ordinary differential equation. That's the first encounter which we have, which we can use to as input and outputs for a neural network training. So we would have a typical x of t plus 1. That's the new time step when we are integrating up a differential equation starting with a given set of initial conditions, plus, and here we would have a time step delta t typically, and this is then multiplied by the way we calculate the derivatives. And I'm just gonna multiply this with the ODE method. So basically what this is doing is that it's calculating a dx dt at a time step x equal to x of t. So if you're thinking of a plain good Euler's method, you would have a differential equation which looks like dx dt equal to some function f of x and t. This function can also depend on higher derivatives, but let's just assume that it depends on x and t only. And then when you discretize, what happens is that t is then discretized into a t. I should actually use a different symbol here. So we would have a time t0, t1, up to a time tn. And that means that this time step delta t is typically defined as a final time, which I call tf in the Jupyter notebook, divided by the number of integration steps which we have chosen. So you can either choose to fix delta t and a final time, and that will give you n by using, for instance, the ceiling function in Python or in any other programming language. And that means also that x is now given by its discretized variant, so x of 0, x1, up to some x of n here. And just to quickly remind you of Euler's method, which is just a Taylor expansion around x plus delta t, t plus delta t. So Euler's method. That means simply that what we have is that we have x of t plus 1, which is the same as x of t plus delta t, just one time step, and that's equal to x of t plus delta t, and we should actually put an approximation sign here because we are truncating at the order of the first derivative, and this goes like delta t times the derivative of f at x of t and this specific variable which we have t. We should actually write this. Let me just rewrite it here. So this should actually be, let me just rewrite this one. So we have a I plus 1, which is the same as t plus delta t because we are now discretizing time. And we have an x of I. So this is the same as x calculated at the time t of I. So this function depends on x of I and t of I. And this function f of x of I, t of I, is actually this d of x, d of t, calculated at t equal to t of I. And the recipe for calculating t of I is given by a t0 plus I multiplied with a delta t. And where I then takes values from 0, 1, 2, and up to n. So this is the standard recipe for discretizing a differential equation. And with that recipe, you can then calculate the updated values. And normally you would do this with a more advanced algorithm than just the standard Euler method. You will typically use something like a Runge-Kutta four-folder. If it's an energy conserving system, you would use something like Euler-Kromers, or even better, a velocity Valais method, and so on and so on. So these are technicalities which we are just going to use in order to generate our data. So let's go back to the Jupyter notebook so that we have everybody on the same wavelength here. So what we're doing now is to simply just call an integrator, an ordinary differential equation integrator, and then produce the data set. So here I'm using this SciPy package, which is called integrate, and it contains this ordinary differential equation integrator. And the first thing is just producing data and spitting them out here, either in files or whatever. And here I'm setting up the parameters which are needed. And I'm setting up an array which defines the inputs and the outputs for the neural networks. So I'm just putting them to 0. And you can see now that this is an array which contains the three spatial dimensions, x, y, and z. And then it contains time here. And then I define the equations to integrate. So this is my Lorentz derivative, which is nothing but what you see here, these three differential equations, which are coupled differential equations. And this is now simply set up here. And you can see it returns sigma times x minus y, rho minus c times x minus y, etc. And it just returns the derivatives. I generate a set of initial values, 100 random initial values, which is this one. And then what I'm doing next is simply to call the integrator here, and this integrates up the equations and returns this x of t, which is now x at the time step t. And down here, I'm simply defining the inputs and outputs for the neural network. So I'm just doing this in a pretty brute force way. I have randomly initialized the initial values, as you can see here, these ones. And then I'm setting up the input and the output for the neural network. So that what I have is, as you can see here, I have an x of t and then an x of t plus 1. So which then contains, this is the input and this is the output. And then we're going to train a neural network with this input to reproduce this output. And this is going to be the first task. We are going then to reuse this one in a application of recurrent neural networks. And we're also going to look at this in connection with autoencoders and eventually also GANs. So the input and output variables are those we will start with, trying our network. And your first task is actually to set up a neural network, either using your own code or TensorFlow or PyTorch or similar libraries, and use this data to make a prediction for the time evolution of a Lorentz system for various values of the randomly chosen initial values. And you should study the dependence of the fit as function of the architecture of the network, which would be a number of nodes, hidden layers, and types of activation functions, and various regularization schemes and optimization methods, like standard gradient descent with momentum, stochastic gradient descent with batches, and with and without momentum. And then you can also have various schedulers for the learning rate, whether you're using something like an ADA-grad, the adaptive gradient, where you're using root mean square propagation, etc., etc. And you find all this information also in the lecture notes, which we had from last week and the week before, and in the program examples, which you find if you go to the weekly schedule here. So if we now look at the GitHub address of the course, if you scroll down and you go to this weekly schedule, you will find the codes for the neural network in the slides for last week and the week before, which is also detailed here. And then there is also a link to a code, which is a little bit more, which is written in a more object-oriented and effective way, which contains all these elements. Or alternatively, you can use your own codes, which you develop from FYS-SDK. You can improve upon them and add more functionality. But the data set which I'm providing here is the one which can be generated by solving this differential equation. Alternatively, if you don't like that, there's another example. And there's a code below here which actually produces the solution of Newton's equations for a oscillatory motion with damping and an applied external force. And that produces also an output, which in turn can be used to train a neural network. So the code which you see here is a simple code which uses a Runge-Kutta forwarder, but it's specialized to a model with a spring force, which also has an applied external force with a cosine periodic function, which drives the motion of the object. And then there is a friction term, which is velocity dependent, which you can see here with v. V is velocity, and x is the position, and t is the time here. And this just implements in a very brute force way Runge-Kutta forwarder for that specific case. And here you would have some specific initial conditions, and you can change to more than one dimension. You can have a three-dimensional spring force, and then you can repeat exactly what is set up in that example you saw previously with the Lorentz attractor. And then in this specific case here, what you would do then is simply to produce an output. So if you look at the output you would produce then, would look something like this as a function of time. So this is x. And then you could use this output from the differential equation solver to set up the inputs and the outputs to a neural network along the same lines as you saw before. So you could actually take this example if you prefer that one instead of the Lorentz attractor, or suppose you don't like anything of what I'm suggesting, you could actually place in your differential equation of choice here. But the thing is that you would need to produce the data like we did here. So this is just a compact way of calling the differential equation solver. And this sets in the value for x of t. And then x of t is then used to define the input and the outputs to the neural network. So this is just a path which I am suggesting and which could form the, how to say, the entry point for the first project. But keep in mind that we want to give you as much flexibility as possible, which means that you can choose the kind of path which is more appropriate for your own research. And just to repeat at the end, I'm in the lectures, we cannot catch all birds with just one stone, which means again that we have to choose a specific path. And since there was a majority of you who were more interested in applying these type of methods to physics-like or differential equations relevant for studies in the physical sciences, we often end up with differential equations then. And then we are going to use differential equation solvers to produce the training data, which can then be used in methods like standard neural networks, recurrent neural networks, which we're going to discuss a little bit later, autoencoders, and generalized adversarial networks. Okay, so any questions, I mean, comments to what I'm suggesting here? Any ideas or things which strike you as, which may strike you as strange or not familiar with, or things which need more explanations? So we could take some time now just to discuss whether this sounds meaningful or not. Feel free to unmute yourself or just ask questions in the chat if you want to. Okay, there don't seem to be any question. Okay,
I have a question.
Yeah.
Because I think at the moment what challenged me is the data preparations to pipe into this the code for the neural network. Would you briefly go through that at some point, or that is still leave for our own explorations kind of thing?
So the you are now thinking of you preparing the data for, let's say, a neural network calculation, or the usage of convolution, because I understood from you that you were probably more interested in convolutional neural networks, right? Is that correct?
I am flexible about that.
Yeah.
But I think the piping part is a bit challenging.
Yeah. So for you, it means that preparing the data set is perhaps the more difficult part.
Mm.
Now, so coming to that part, since this becomes very specific for us, a certain data set, this is something which we will not discuss in the lectures.
Mm.
So that means that you would have to think on how you can prepare the data for a training with a deep learning method. Like if you look at the differential equation path and the first path, so this is something which can be combined, actually. If there's somebody of you who is more interested in the computational path and want to just use whatever data set, the differential equation path is a way where you actually, this is where we generate the data. And you can see now, if you look at this function here, at the end, what we are doing now is we are taking the results from a differential equation solver, which gives you just an array of data for X, Y, and Z, the position, or whatever this is, as a function of time. And then this is prepared as input to a neural network. So this is already you preparing the data, but we have specialized that to a specific case. But if you have other data sets, this is something where we would have to rely on somebody having prepared the data for you, or you preparing the data yourself. So we could, as an alternative here, we could also have a path where you also need to prepare the data and then feed that into a deep learning method. So we've had cases with master degree thesis where people actually spent most of the time on preparing the data. This is often the most difficult part. So in a certain sense, this is a kind of vanilla data set which I'm producing here, which is easier than many other data sets. And you already have the data prepared here. So the only thing which is missing, which we will also discuss a little bit next week, is our examples on how to run let's say, a deep learning model with this data set as input.
I have one more question.
Yeah.
So since I think last week I mentioned about the challenge from the dimensionalities is one of the challenge that I'm facing from data preparations.
Yeah.
In that case, I know you might not be able to go through that in the class, but is it possible, like schedule and extra time if I have a problem with that?
Absolutely. So we are also going to discuss what we call dimensionality reduction methods. So this is a topic which we are going to bring up in connection with autoencoders. So autoencoders are a way to reduce the dimensionality of the problem. That means that we're also going to mention methods like principal component analysis, which is a way by which you can reduce the dimensionality of the problem. So if you look at these differential equation solvers and the way we are going to plug them into a neural network, this is going to give us a model with tons of parameters and what we would call a high dimensionality in the variables to optimize. So we will be looking for ways to reduce the dimensionality of this data set. So I'm going to use this differential equation type of problem, because that's what's close to my own research, as a way to demonstrate dimensionality reduction methods. So these are topics which we will discuss and touch upon. So autoencoders are unsupervised methods, which in practice mimic what dimensionality reduction methods like principal component analysis is doing. So we will touch upon these things, definitely.
Yeah, and in that case, I have just one last suggestion. If you're going to talk about the PCA kind of things, can you also talk about what happens if this kind of clustering doesn't work, because sometimes the data can be very messy, and in reality, there are a lot of things that is falling out from the predictions.
So you have to.
Thank you.
We will touch upon that, but we can also have the more individual sessions here, if that is more relevant, because the people have. We are something like I see we are something like 18, 19 registered people for the course, and that means that there are many needs and wishes, and for some of the cases we will not be able to cover that in the lectures, and then you would have to be more on your own. And that's also the kind of basic idea behind the self-study course. Okay. Any more questions, guys? Things which are unclear, you want to bring up? You also feel free to send me just a message, and then we can always try to tailor things to your own interests and research problems. But this is a kind of a recurring topic which I want to bring up as an example. And as I said to you, this is close to what I'm normally doing here. And the first, actually, when we come to convolutional neural networks, since there are people among you who are more interested in classification problems, and in particular, classification of images, this is one of the, this is the leading method. And it is also a dimensionality reduction method. So just keep in mind this word, or concept of dimensionality reduction. So the problem we always struggle with any type of data sets from the physical sciences or from whatever kind of field is the fact that the dimensionality becomes quickly huge. And we also want to find ways to reduce the dimensionality in a meaningful way. So convolutional neural networks have also been applied to regression problems where we want to find a continuous function, but the main area of success has been on images. And it's one of the, what we might say, the central methods which demonstrate a spectacular success for deep learning methods. And we have data sets like ImageNet, which contains millions of images, which have been used to pre-train convolutional neural networks. And they contain images of houses, cars, bridges, animals, whatever. And the networks have been then trained to reproduce these features here. If you look at many images, if you take an image of a house, a typical example of a house then is that you are not interested in the in keeping information about everything of the house. If you have an image, you are, for instance, not interested in having pixels which represent parts of the wall of the house, because that has the same painting. So you can actually reduce that, and you can focus more on the corners of the house. You can focus on windows, doors, and things like that. So you can actually reduce the dimensionality and still be able to recognize this as a house. So the key recipe here, or the key overarching topic is dimensionality reduction through convolution as a mathematical process, which in essence means us having a filter which reduces the dimensionality of the image itself. So what I wanted to give you first is just some pros and cons, and why we would use convolutional neural networks and how we can use them. And then we're going to look at several of the mathematical aspects of a convolutional neural network. We will most likely dive into this for next week as well. And then we are going to look at how we can set up codes for convolutional networks. And this applies to the path number 1 in the project. If you wish to write your own code, this could be a challenge by itself. Alternatively, for those of you who want to use convolutional networks, I would normally recommend to use these libraries like TensorFlow provided by Google, or PyTorch, which comes from Facebook/Meta, etc., etc. Okay, so they're very similar to ordinary neural networks. So the difference is that they make CNNs make explicit assumptions about the inputs, and that the inputs are images, which allows us then to encode certain properties into the architectures. These then make the forward function more efficient to implement and vastly reduce the amount of parameters in a network. So if you think of a standard neural network, what we normally have then is what we call dense encoding, which means that we are dealing with a matrix, for instance, which contains all the weights and biases of the model which we have. And then we are performing affine transformations by multiplying a dense matrix with another dense matrix, eventually a dense matrix with a dense vector. So the question is, can we reduce the connectivity between different layers in a meaningful way? And this is the kind of overarching message about a convolutional neural network. So they have had an extreme success, and it's the method of choice if you're doing images. I should also say that if you're used to imaging with singular value decomposition methods or Fourier transforms and things like that with functioning as filters, if these methods work well on your data, there is no point in jumping into a CNN modeling. But if you have data with tons of images with tons of pixels, which are not easy to handle with standard methods like singular value decomposition and Fourier transforms, then convolutional neural networks are actually the method you should think of. Now I see we have passed the hour, so let's take a small break, guys. And what I want to do in the first part of the second lecture today is to go through some of the more overarching topics with a CNN. And then I wanted to remind you about the mathematical process of convolution, what that actually means. So you can think of convolution the way we are going to implement it as an efficient matrix or matrix vector multiplication, where only specific features are retained. So when we look at, for instance, images, or this could be sound files or medical images from CT scans and so on, what we have are some specific important properties. And one, they are normally stored as multidimensional arrays. So if you think of the pixels of a figure, you have 3 color channels. And if the figure has, let's say, 100 pixels times 100 pixels, and that's the resolution of the image, then you have 100 times 100 times 3 color channels. So that means a matrix of dimensionality 100 times 100 times 3. This is actually a tensor, or just generally we just call it for an array. And you can obviously reduce this dimensionality because there may be information in this image which is not relevant, like the color of a house is not something you would keep as a kind of high resolution type of information in an image. One axis of the image is typically called a color channel, or the channel axis used to access different views of the data. So red, green, and blue channels of a color image, or the left and right channels of a stereo audio track. So these kind of way to encode information is not limited to images only. It can also be used on, let's say, recognition of speech and soundtracks. So when you perform an affine transformation in a neural network, a standard neural network, you're actually keeping all the possible information. So that means that there are properties which are not exploiting. And in a neural network, you end up with a dense matrix multiplications, and all the nodes in a typical neural network would be connected from one layer to the other layer. And that clearly increases the dimensionality of the parameters which are needed to study. So if you now look at this example here, you can quickly get an understanding and a way to appreciate the increase in dimensionality. So if you consider an image of size 32 times 32, and then you have 3 color channels, the standard ones. If you now want to connect a single fully connected neuron in a first hidden layer of a regular neural network, that would have something like 32 times 32 times 3, 3072 weights. And it still seems manageable, but clearly you're going to have many images. If you have millions of images, this is going to blow up. If you want to have an image of a more respectable size, let's say 200 times 200 times 3 color channels, that would need to that neurons that would have something like 120,000 weights. And then you could have many such neurons, and the parameters would add up quickly. So typically, if you have an input layer, and suppose the input layer now has, let's say, 100 inputs, and you have 100 hidden nodes, that gives your matrix already a dimensionality 100 times 100. And then these are connected with different hidden layers. And the more hidden layers you have, the more parameters you need to define. So a typical standard feed-forward neural network, which we discussed last week and the previous week, that is represented mathematically by a series of matrix vector multiplications, which then are represented by dense matrices, which keep all the information. And clearly that is going to lead to models which are very, very CPU intensive to train. So the whole thing with a convolutional neural network, that they take advantage of the fact that the inputs consist of images, and they constrain the architecture in a more sensible way, as we will see here. So to understand it better, with the above example, you could now think of these neurons in a layer will only be connected to a small region of the layer before it, instead of all of the neurons in a fully connected manner. So the final output layer could, for instance, just contain a dimensionality of 1 times 1 times 10. So you could have a series of operations here, where you have the original input layer, and then the image may be reduced through some filtering. You produce a new set of images, which are then trained through the network. And then this produces a final output, which has been further compressed. So we're going to look at the mathematics of this first, and then we are going back to how we can set up a neuron network with convolutional neural networks. So there are topics which we need to discuss a little bit more now. So this kind of compressing of an image could then contain an input layer where you have the raw image, and then there is a convolutional layer where you perform the filtering. Then this produces an output, which is then sent through a rectified linear unit. So the convolutional layer contains a set of parameters which need to be trained, and this is normally done by standard backpropagation. Then with a ReLU layer, you produce a output in the same way as you would have with the final output layer in a standard neural network. Then this is fed into what is normally called a pooling layer, which performs a further downsampling of the dimensionality. So you could reduce, for instance, the dimensionality from 32 times 32 times 12. This could be reduced down to 16 times 16 times 12. And then this could now be fed into a fully connected neural network, where you then would produce further compressions of the image and produce a standard training by a standard neural network here. So what we're going to look at first now is I'm going to skip some of this here, but I wanted to focus a little bit more the mathematics of CNNs, so that you can see what is going to enter in the setup of a convolutional neural network. So basically, for those of you who are also familiar with the imaging and the filters and filtering, like Kalman filters or usage of Fourier transforms or similar operations, the mathematical operation of interest is actually the process of convolution. So convolution is represented by mathematical operations on two functions in order to produce a third function that expresses how the shape of one gets modified by the other. So the typical idea then could be something like what you see here. So you could now think of this x representing the position of an object. And this weighting here could be a way to weight specific positions. So you could imagine that the positions, the measurements you make are noisy. And then there is a function w which filters away the noise for you and then produces a final output. So this kind of integral, if you have a continuous function y of t, continuous function x, and a continuous function w, they are used to filter out specific information. And this is pretty common in imaging or filtering out of noise, etc., etc. And probably some of you have met this in connection with Fourier transforms. So the above integral, which you see here, is normally written out in a more compact version like this. So you have this x and then asterisk times w, which means that we have performed a convolution. So convolution, you can think of that as the original data set x of a, and then being multiplied with a weight function, which may filter out some specific properties. Okay, so the discretized version of this, if this variable a goes from minus infinity to plus infinity, would then be to set up a function like this. So computing the inverse of this convolution is known as deconvolution. And the question is, how can we use this and what does it mean? So in order to gain some kind of information about the or kind of understanding of what happens, so let's look at a polynomial multiplication here in order to figure out how we can rewrite that in a smarter way. You will also see that convolution itself is nothing but a smarter matrix multiplication. And you will see that in just some few moments here. So if we look at the polynomials, so we could take a polynomial of second order and a polynomial of third order. And we know that when we perform a multiplication of these two polynomials, since this is second order and this is third order, the final polynomial should actually become a fifth order polynomial where we have these unknown parameters, delta 0, delta 1, etc. The way we would set this up in an efficient way is not to write pt times s of t. That would be a very inefficient way of doing the polynomial multiplication, but rather what we would do now is simply to reorder it, and you will see now that delta 0 would simply be given by this term. Delta 1, actually, this is a typo which I've forgotten to change. This should be alpha 0 times beta 1 here, the second one. So let me take a note of that one and remember that, because that is a typo I've thought of changing, but I've forgotten to do it. Okay, so that's a small typo here. Anyway, the other parameters is delta 2, delta 3, delta 4, and delta 5, which we have here. They can all be expressed in this more compact way. So you see now that except for alpha equals 0, and except for I, and for beta, so we note that alpha I is equal to 0, except for these values, and beta I is equal to 0, except for I equal 0, 1, and 2, and 3. And you can write the coefficients delta j using a discrete convolution. So that means that you could rewrite it like this, and you have a sum of I here, and then you would rewrite this in a more compact way like a asterisk beta, or for coefficient for the subscript j here. You could rewrite it as a double sum with a restriction that L is I plus j. Now there are some potential drawbacks here, in the sense that these two these indices here, they run from -infinity to +infinity, and we wouldn't like to do that. So the above can actually be written out in a more compact way. So you could think of setting up a matrix for the alpha and the beta values. So you could have a matrix for the alpha value, which is written like this. So this is a 4 times 6 matrix, and this is a vector of length 4. So we will have a 6 rows and 4 columns, a 6 by 4 matrix, and this is multiplied by a 4 by 1 vector here. So this process is actually what we call commutative, and you can easily see that you can rewrite this in terms of a matrix holding beta and a vector holding alpha only. And this is now given by this more compact notation here, which now represents a 6 by 3 matrix multiplied by a 3 by 1 vector. And you see that the dimensionality here is also smaller. So this is the kind of approach which you would choose when you're setting up the calculation of these parameters delta. And this can then be represented, or this is just one way of representing the mathematical process of convolution. So you would write this operation in terms of this A with asterisk beta, and then you have the specific subscript J here. You could encode it in terms of a single sum or just as a double sum here with a restriction. And you could obviously put in further restrictions where you limit the number of values. If these values alpha I and beta j are 0, you could simply have an if test here which says that then it's not. Or you could actually put in the actual limits if you know where the values are non-zero. But this is just a way to represent convolution in terms of a matrix vector multiplication. And I'm introducing these examples here as a simple prelude to what is going to come now when we are introducing filters. So another example which many of you may have met, and this goes back to the simple example which we looked at in the previous lecture, where we're generating the data for the harmonic oscillations. So this is actually the type of equations. And if you have a driving force here, you can find a particular solution to each of these components f of n with a given x here. And a particular solution for the entire driving force is then given by a series which looks like this. And then you have the principle of superposition, where you know that since this is a periodic, there is a periodic solution for this model. It means that the solution repeats itself after a given period. And in this, what you find down here is a simple, the usage of Fourier transforms, which is another example of setting up a convolution process. So I'm not going to repeat all these things. You can just look up the way you calculate the coefficients and the way you set up the final Fourier transform. So these are all examples of the mathematics of convolution. And normally what we end up doing is that we have either two-dimensional or higher dimensional objects represented by images. And we often use convolutions over more than one dimension at a time. So if we have a typical two-dimensional image as an input, so this would be an image with a specific number of pixels, then we can have a filter which is defined by a two-dimensional kernel k. And this kernel could be given by this function here, k. And then we will take the convolution of I and k and find the final representation or the output of this image through the process of convolution. And again, convolution is a commutative process, as you saw from this simple example of a polynomial multiplication. And you can reverse the order of the way you set up the operations. So you can do the same thing here. So you can rewrite the input in terms of I minus m and j minus n, and similarly multiply with a filter here. The latter, as you saw also from the simple example of a polynomial multiplication, is normally easier to implement. And in a machine learning library, you often implement this in terms of matrices which are called Toeplitz matrices. And we are coming back to that. So this would be the some of the standard procedures for setting up the type of dimensionalities which we are interested in. So if you think of the dimensionality problem, when you're designing these filters, one of the reasons why we introduce convolutions is that we want to reduce the dimensionality of the problem. And you should keep in mind that these convolutions, which we're doing, are often handcrafted. That means that you can apply specific filters for specific types of images. So sometimes you may be interested in edge detection, you may be interested in frequency reshaping or other types of operations. So just keep in mind that many of the networks which have been trained, they are actually handcrafted. So this is important to keep in mind. If you use ImageNet, that has been trained on millions of specific images, and you can have similar other data sets. Like I've been using convolutional networks to identify outputs from specific experiments in subatomic physics. And in that case, I have often trained an initial neural network or convolutional neural network based on simulation data. And then based on this simulation data, I have then obtained a pre-trained network, which I then have applied to data which were not included in the pre-training. And then, depending on the kind of results I have often a classification problem, and I want to classify specific events from a reaction in subatomic physics, whether there is an alpha particle which is emitted, or proton which is emitted, and other particles which are emitted from a specific reaction mechanism. So keep in mind that these are often handcrafted. So suppose now, if you look at the dimensionalities here, you can quickly see why a standard feed-forward neural network leads to dimensionalities which can be monstrous. So if you assume that you have an input vector of length 10 to the 6, then you can construct a neural network with only one hidden layer. And this has with 10 to the 4 nodes. So that means that you will have a weight matrix which contains 10 to the 10 weights to be determined, together with 10 to the power of 4 biases. So that means that your number of parameters, if you assume that you have an output layer, which is meant to train whether the sound sequence represents a human voice, true, or something else, then you have only one output node. But the output node connects to 10 to the 4 nodes in the hidden layer. And then there are in total 10,000 weights to be determined. But anyway, the number of parameters to be determined in this not very deep network is actually 10 to the power of 10, which is a monstrous number of parameters. So in today's architectures, you can train such neural networks. However, there's a huge number of parameters for the task at hand. In general, it is a very wasteful and inefficient use of dense matrices as parameters. And this is where this filtering comes in. So let's try to look at some of the basic mathematics which is involved, because that leads also to specific parameters which we have to define when we are setting up a convolutional neural network with specific filters. So just keep in mind this, the networks are often pre-trained or handcrafted in a specific way. If you're doing a physics experiment, you may often have some simulation data, some theoretical simulations which you trust, and you can easily use these to pre-train such a network. And then with a pre-trained network, hopefully that makes it easier from a computational point of view to train on the real data which you produce. In some cases, you can have a mix of real data and simulation, and that would make up your data set. Okay, so let's go back to the whiteboard and try to set up the some of the basic operations which we're going to deal with. So let's just do that. So we're just going to call this the basics of CNNs. And we are going to need some time next week as well. So basics of CNNs. So let's now look at the input data set, which is given by a matrix of dimensionality 3 times 4. So we have an input here, and I'm going to write this like this. So we have the input variables, and I just call them A, B, C, D, not very exciting, E, F, G of H, and then I have I, J, K, and L here. So these are some specific values. And then I have a filter here, so which I call for W, or weight function. And in my case, I have a 2 by 2 filter only. So W, and it has X and Y and Z here. So this is a 2 by 2 matrix, and this is a 3 by 4 matrix here. Now, what I'm going to do now is to produce an output through this filtering, where I'm going to perform the process of convolution by acting with this filter on only specific subblocks here. So the first thing I'm going to define now is a hyperparameter, which is called the stride. And this stride is given by 1. So when I'm doing the filtering now, what it means is the following. So if you now put some coloring here, so I'm going to perform the convolution process on this object here first. So this is going to give me a box here where I now multiply the elements which I have in the input matrix with the weights. So that means that I have the multiplication of A with W. So I'm just setting up the filtering process with convolution. And I have B times X, and I have E times Y, and F times Z. So I'm simply implementing the definition of convolution for a discretized object. So this means that I have a block here which looks like A times W plus B times X, and I have E times Y plus F times Z. Now, when I say stride equal to 1, that means that when I'm now setting up my next block here, I'm actually going to move here just with 1 unit. So it means I get into this yellow region here. So stride 1 means simply that I am moving 1 step, and that produces a new block here. So yellow is not the best color to use actually. So I would have a B multiplied with W plus a C times X plus F times Y plus G times Z. So this is my stride equal to 1 when I'm now setting up this matrix convolution. That means that the next step here, if I now use a green color, so my next one would simply be this block here. So that would be along the columns. So I would have a new block here, which looks like C times W plus D times X plus, and then I have G times Y plus H times Z. And then since I have a stride equal to 1, my next operation, which I need to do now, is to perform a step down. I've gone through the columns for the first row here, and now I would have this block, which comes down here. So what I'm doing is simply to set up the process of convolution. And when I perform the multiplication here, what I have is E. So let me just keep everything up here. I have a E times F of X plus I times Y plus a J times Z. Then I have the next block. Now I'm running out of colors soon. The next block is this one. So we're going to mark this in dark blue here. So we have an F times a W plus a G times X plus a j times y plus a z times k. And finally, I have the last block here, which I'm going to mark with this color here. So this is the final one. So that gives me this block, which is a dark green. So I would have g times w plus h times x plus k times y plus l times z. So this produces at the end a reduced dimensionality. And you see that the dimensionality here is now a 2 times 3 matrix. So I started with a matrix which was a 3 times 4. And through this filtering process, I've now found a matrix which is a 2 by 3 matrix. Now, the one thing you should note here, when you look at this type of operation, which we did with a stride equal to 1, or we can have a stride equal to 2, etc., etc. If you look at the output size, which we have, you have a simple rule with this operation here. So we would have now a stride equal to 1. And we have a matrix which, if we now assume output, assume a symmetric matrix, because that makes it a little bit easier to look at, a symmetric matrix. So assume now you have a dimensionality n. And let's say that this dimensionality is, just to give an example, 7. So we have an input matrix, which is a 7 by 7. Let's assume that. And then we have a filter. Assume a filter of dim 3 times 3. So that means that we have a dimensionality f, which I put equal to 3 here. So the filter has full dimensionality 3 times 3. So that means that the output size is something which I can calculate if I assume they are symmetric. Square matrices. So the output size is something we can set up immediately as this n minus the filter size divided by the stride which we have plus 1. And if you have this 7 by 7 matrix, and you have a matrix, a filter matrix, which is a 3 by 3, and you do a stride, which is 1. So if we now set n equal to 7, f equal to 3, and stride s equal to stride, and we put that one to 1, you see that in this case, we would now have 7 minus 3 divided by 1 plus 1. So that gives us 5. So that means that we get a 5 by 5 output. Now, if I take the previous case, which was not symmetric, I could try to make that symmetric. So I would have a 4. I could take a 4 by 4 input matrix and a 2 by 2 filter. So I would have 4 minus 2, which obviously gives 2 divided by 1, which is 1. And then I would have a plus 1. So that would give me a 3 by 3 matrix. So I could actually, if I have a 4 by 4 matrix and a filter by dimensionality 2 times 2, I can reduce the image to, or the object to a 3 by 3 matrix. Now you can increase the stride. So you could now assume that we still have this case with n equal to 7 and f equal to 3. And then we could put a stride, which is equal to 2 here. So let's see what happens then. If I do that, then I have 7 minus 3 divided by 2 plus 1, and this is equal to 3. So that's still doable. That means that instead of a 5 by 5 image, I get a 3 by 3 image. If I take a stride s equal to 3, then I will not get a whole number, which means that I cannot have a stride equal to 3 here, because then I would get something which is 7 minus 3 divided by 3 plus 1, which is 2.33. And we cannot define a matrix which has dimensionality 2 times 3 2 times 3. So this is not possible. So the stride is also a parameter which is used in order to reduce the dimensionality of the problem. So when you do convolution, stride becomes one hyperparameter which you would typically have to tune. So let's just mark that one. So stride here, that becomes a hyperparameter to train. Now, there is another thing which we need to think a little bit about. If we now look at this matrix here, which we put up, this 3 by 4 matrix, which is then filtered with a 2 by 2 matrix. If you now look at the variables which you have in the final output, what you will see then is that this variable A appears here, and it appears in nowhere else. So this A appears only here. On the other hand, W is everywhere, is here and here and here, etc. So from the original image which we have here, this variable A appears only in this matrix element. B, on the other hand, if you look at B here, so B appears both here and here. And other variables like this C, so C appears here, C appears here. So that appears in 2 places. So what is common then is to introduce another hyperparameter when we do the filtering. And this hyperparameter is normally called padding. So an additional hyperparameter which you will encounter in order to allow certain features of the image to appear in more than just one matrix element of this output matrix. So an additional feature, which is an additional hyperparameter, which is normally included, hyperparameter is called padding. And this becomes an additional parameter which we need to include in the training of the network. So this is normally called P. And what that means is that if you take the original matrix which we had, so this can contain many entries here. So I'm just writing it like this. What you could do now is to set up an additional outer padding, so which could go like this. So this would be, if we have just one additional row and column here, this would be a padding equal to 1. What happens then is that we're just putting in zeros in all the positions here. But then when you perform the convolution, what will happen then is that this matrix element which we had earlier, this specific matrix element like this one, that would now appear in more than just one slot. And you can easily see that when you perform the operation. You can increase the padding if you want to. So this is a way to actually have more slots in the output matrix which contain information about the input matrix. So in the previous case, what you saw now is that this information about A was only kept in this first slot, whereas B, for instance, and the other parameters, except for the corners here, they are just parameters which are now included in more than just one of the matrix elements. And this is something which we then typically want to avoid here. So if you look at another one of these corner parameters, like this L here, this appears only here and in none of the other ones. Actually, this one is not L, this is the E. And you can see that, for instance, E is a variable which also appears in only in one of these elements here. So E, which is one of the corners here, appears only here. The same thing applies to I, which is also one of the corner elements here. So by adding this padding, the idea is that we can keep information about the input in more than just one matrix element when we are doing the convolution process. So the convolution process then can consist of many such filters actually, and we are going to see some of these structures when we discuss next week. But I just wanted to bring up some of the additional hyperparameters which are typically involved in this process of convolution. Now, convolution is actually nothing but an efficient matrix vector or matrix multiplication. In order to see that, let's now take a look at what is taking place when we now have a specific matrix as input. So convolution, the way we are setting it up, and the way it's normally expressed in our codes is nothing but convolution as an efficient, as another, or just as another way of doing a matrix vector multiplication. Matrix and matrix vector multiplication. So let's try to see what is going on here. So let's look at an example. Suppose we have an input matrix, which is a 3x3 matrix. So we would have an input element I00, I01, and then we have I02 here. We have an I10, I11, and I21. And finally, we have I20, I21, and I22 here. And this is now being convoluted with, so I'm just writing this process like that, the process of convolution. And this has now a filter, a 2x2 filter. So I start with a 3x3, and then I have a 2x2 filter, and I'm going to do a stride equal to 1, and I have 0 padding, and P equals 0. And then I have a filter here with W00, W01, and new W10, and W11. So the filter itself has parameters which need to be trained. Now, when we now perform the process of convolution here, this is now going to give us the following. So when I just write it straight out, it's going to have I00, this is not very exciting, plus I01 with W01. I have my I10 multiplied with W10 plus I11 multiplied with W11. So that's one of the slots, that's that matrix element. And then I continue, and now I'm doing a stride equal to 1, which means that my next block, which I'm looking at, is this block here, and then convoluted with this filter matrix here. So that means that what I have then is an I01 of W00 plus I02 of W01 plus I11 of W10 plus I12 multiplied with W11. As I promised you, this is not the most exciting thing we are doing here, but I wanted to demonstrate how I can rewrite this in a more efficient way as a matrix times a vector. And this would now contain the next block, so which is nothing but this part here. So since I have stride equal to 1, then this is now convoluted with that one. And you can easily see now that the matrix which I get should be a 2x2 matrix if I use these rules for setting up the final dimensionality. So I have an I10 multiplied with W00 plus an I11 multiplied with W01 plus an I20 multiplied with W10 plus a W11 multiplied with I21. And the final one is I11 multiplied with W00 plus I12 multiplied with W01 plus I21 of 10 plus I22 with W11. Now, what we can do now is to actually rewrite this as the process of convolution with two matrices, which we can actually rewrite. So you can think of a vector here. One of them is a vector. So I could define now a vector I of length 9, which has the following elements: I00, I01, I02, and this goes all the way up to I10. So I'm just writing out all the elements of the input matrix as a vector. So I'm flattening it out. And then I have I1, says I12, and then I have I20, I21, and the final element is I22 here. So this has a length of 9. And I'm now going to define a matrix here, a matrix W, which I'm going to rewrite like this. And you can see that I can have a matrix which goes like W00, W01, and then I have 0, and then I have a W10, a W11, and then I have 0, 0, 0, and 0. And then I can repeat this and have a W00, a W01, there's a 0, I have a W10, W11, and then 0, 0, 0. And this gets repeated in the following way. So I get now a W00, a W01, there is a 0, and there's a W10, and W11. And this is again repeated. So I have a 0, and then I have a W00, W10, and then there's a 0, 0. So this should be at the end a matrix which has dimensionality 4 times 9. So this W has dimensionality 4 times 9. And what I can do now is to, when I write this out, this operation here, the convolution process is the convolution between this matrix I, W prime, with this vector I. And this is now going to give us an output matrix, so O for output, which has no dimensionality or length equal to 4. And length equal to 4 is now us taking this product, which you see here, rewritten as a vector. So every vector element is now given by this specific matrix element. I can what I'm doing here, I'm flattening out this matrix. So I can actually rewrite the process of convolution as one vector which contains the input variables, and one weight matrix which is now written as a sparse matrix. And next week we are going to look at how we can actually encode this in a smart way. So this type of matrices which you see are normally called tuplets matrices. And we are going to look at the structure of these matrices a little bit closer next week. So I see I think there is a 1, 2 here, there, right? Yeah, let me see. 1, 2.
Yeah, it was above, but I think you carried out correctly afterwards.
Okay. So I'm just gonna. You will find this one wrapped up in my my lecture notes as well. So all these kind of details. And next week, because I see that my time is over here, I'm sorry for going through some of these kind of details in a meticulous way, but I wanted to show you how you can actually transform your data in terms of operations with matrices and vectors, and represent convolution in terms of a weight matrix, which we are going to define as a so-called tuplets matrix. And we are going to see then next week how we can view convolution as a special type of matrix vector multiplication, where we have a so-called banded tuplets matrix. So this matrix W prime is a so-called banded tuplets matrix. So next week, in addition to these hyperparameters, which we have defined, padding and the stride, we are going to look at how we can set up a convolutional neural network linked with the mathematics of convolution, which we now have re-expressed in terms of a modified vector matrix multiplication, which we will discuss in more detail next time. So this is more just to prepare some of the basic mathematics for convolution, the way it's actually implemented in convolutional neural networks. So what you should keep in mind is that many of these convolutional neural networks, they are trained on specific data sets, and they're really handcrafted. So next week, we're going to continue with the details of convolutional neural networks. And for those of you who want to use convolutional neural networks in the project, you can decide on two different paths depending on what you want to do. Some of you may have data you want to analyze with convolutional neural networks, and then you can easily set up the analysis of this data using, let's say, TensorFlow or PyTorch, which we would recommend in that case. Alternatively, if you wish to, you could follow this computational path where you write and develop your own code for convolutional neural network. So next week, I'm going to give you more of these details based on this mathematical understanding of convolution, so that you would have all the elements for setting up a simple convolutional neural network yourself. Alternatively, better understanding how you define the parameters and which parameters you have to specify when you're using, let's say, TensorFlow or PyTorch.